Linear Algebra 2, Tutorial 2, Basis and Transformation Matrices. Problem 1. Find some vector x in R3 such that the vectors x, v, and w form a basis of R3. So here v is the vector 1, 2, 3, and w is the vector 0, 7, 1. Solution. We will look for x in the form x1, x2, x3, just an element in R3. So since we have three vectors, we know that the dimension of R3 is 3, and each basis of R3 thus has to contain three vectors. So our candidate for a basis contains three vectors x, v, and w. So since we have three vectors, we know that they will form a basis of R3 if and only if the determinant of the matrix which we obtain when we write the coordinates of these vectors into columns, so this determinant should be non-zero. So in our case, we are talking about the determinant of the matrix. So column-wise, we have x1, x2, x3. These are the coordinates of x. 1, 2, 3. These are the coordinates of v. And 0, 7, 1. So these are the coordinates of w. So let us compute this determinant. So this determinant is equal to the following expression. So we have x1 times 2 times 1 plus x3 times 1 times 7 plus 0 times 3 times x2 minus 0 times 2 times x3 minus x1 times 3 times 7 and minus x2 times 1 times 1. So in this expression, we see that we have 2x1 minus 21x1. So this gives us minus 19x1. And then we have minus x2 here. So here we have 0 at x2. And we have 7x3 here. And here we have 0 for x3. So we have that our determinant equals the expression minus 19x1 minus x2 plus 7x3. So this expression is non-zero, for example, if we take the following non-zero vector, x1 is equal to 1, x2 and x3 are equal to 0. So then the value of this expression is minus 19, which is non-zero. So answer, we can take as this additional vector x the vector 1, 0, 0, and then the vectors x, v, and w form a basis of R3. Please note that this answer is not unique. We could have taken x1 is equal to 0, x2 is equal to 1, and x3 is equal to 0. Or there are many other choices for the vector x. So this is just one of the possible answers. Problem 2. Let n be the subspace of the space of all real polynomials of degree at most 3, consisting of all polynomials f of x, such that the value of f at 1 is equal to 0 and the value of f at 3 is equal to 0. Find a basis of n and extend this basis to a basis of the whole space Rx sub 3. Solution. Consider an arbitrary polynomial f of x written in the standard form a plus bx plus cx squared plus dx to the power 3. So this is an arbitrary element in Rx sub 3. The value of this polynomial at 1 is equal to a plus b plus c plus d. And the value of this polynomial at 3 is equal to a plus 3b plus 9c plus 27d. Therefore, the polynomial f of x belongs to n if and only if the vector a, b, c, d of coefficients of this polynomial in the standard basis. So this vector should be a solution to the homogeneous system of linear equations with matrix 1, 1, 1, 1. So these are coefficients here in f of 1. And then the second row is 1, 3, 9, 27. These are the coefficients here in f of 3. So in order to determine a basis in n, we need to solve this system. So we start from this matrix and we reduce it to a row echelon form using Gauss elimination. So we start with our matrix. We have 1 in row 1, column 1. So we use this one to eliminate all other elements in its column. So we subtract row 1 from row 2. Row 1 remains the same, and row 2 becomes 1 minus 1 is 0, 3 minus 1 is 2, 9 minus 1 is 8, and 27 minus 1 is 26. So now we see that in the second row all elements are even, so we can divide the second row by 2. The first row remains the same, and the second row becomes 0. Then 2 divided by 2, 1. 8 divided by 2 is 4. And 26 divided by 2 is 13. And now we have 1 here in row 2, column 2. We can use it to eliminate all other elements in its column. So we subtract row 2 from row 1. Row 2 remains the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 4 is minus 3, and 1 minus 13 is minus 12. So we have 2 linearly independent rows in this row echelon form and 4 unknowns. So this means that we will have 2 linearly independent solutions where we can take the unknowns which do not correspond to the leading elements as parameters. So the unknowns which do not correspond to the leading elements are C and D. So we take C and D as parameters, and from the first row we can write that A is equal to 3C plus 12D, and from the second row B is equal to minus 4C minus 13D. Plugging in C is equal to 1 and D equal to 0, we get the solution 3 minus 4, 1, 0. Plugging in C is equal to 0 and D is equal to 1, we get the solution 12 minus 13, 0, and 1. So all solutions to our system are linear combinations of these two, and these two solutions are linearly independent by construction. Therefore, the corresponding polynomials, so for this vector we have the polynomial 3 minus 4x plus x squared, and for this vector we have the polynomial 12 minus 13x plus x cubed. These two polynomials form a basis of n. Finally, we need to extend this basis to a basis of Rx sub 3. To do that, we write the coefficients of our two polynomials as columns in a matrix. Here, then we write the vertical line, and then we append the identity matrix to the right of it. So here are our two basis vectors which we want to extend, and then we write the identity matrix next to it on the right. And we try to reduce this matrix to a row echelon form using Gauss elimination. So we need only a weak row echelon form here. So because of this part 1, 0 and 0, 1, we start by swapping rows 1 and 3 and swapping rows 2 and 4. So row 3 becomes row 1 in the new matrix, row 4 becomes row 2, original row 1 becomes row 3, and original row 2 becomes row 4. So now in this matrix we have 1 in position 1, 1. We can use it to eliminate everything else in its column. So we subtract 3 times row 1 from row 3, and we add 4 times row 1 to row 4. Rows 1 and 2 remain the same. Row 3 becomes 3 minus 3 is 0, 12 minus 0 is 12, 1 minus 0 is 1, 0 minus 0 is 0, 0 minus 3 is minus 3, and 0 minus 0 is 0. And row 4 becomes minus 4 plus 4 is 0, minus 13 plus 0 is minus 13, so 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 4 is 4, and 0 plus 0 is 0. So now here we have 1 in row 2, column 2, so we use this 1 to kill everything else below it. We need only weak form. So we multiply row 2 with minus 12, and add to row 3, and we multiply row 2 with 13 and add to row 4. So the first two rows remain the same. The third row becomes 0 minus 0 is 0, 12 minus 12 is 0, 1 minus 0 is 1, 0 minus 0 is 0, minus 3 minus 0 is minus 3, and 0 minus 12 is minus 12. And the last row becomes 0 minus 0 is 0, minus 13 plus 13 is 0, so 0 plus 0 is 0, 1 plus 0 is 1, 4 plus 0 is 4, 0 plus 13 is 13. And now we see that we have a matrix in a row echelon form, with leading elements being in columns 1, 2, 3, and 4. So column 1 corresponds to the polynomial 3 minus 4x plus x squared, this one. Column 2 corresponds to the polynomial 12 minus 13x plus x cubed, this one. Column 3 corresponds to the polynomial 1, the first element in the standard basis. And column 4 corresponds to the polynomial x, the second element in the standard basis. So these four polynomials form a basis of Rx3. This is our conclusion. Problem 3. Let V, consisting of V1, V2, and V3, be a basis of some vector space V. Consider the following elements in V. The element U1, which is equal to V1 plus V2 plus V3. The element U2, which is equal to V2 plus V3. And the element U3, which is equal to V3. Prove that U, consisting of U1, U2, and U3, is a basis of V. Determine both transformation matrices from V to U and from U to V. Express all VI's as linear combinations of the UJ's. And for the vector x in V, whose coordinates in the basis V are 1, 2, and 3, determine the coordinates of this vector with respect to the basis U. This should be U, not W. Solution. Let us start with expressing the VI's via the UJ's. If we look at the last equality, we immediately see that V3 is equal to U3. This is exactly the last equality. If we plug in that V3 is equal to U3 into the second equality and move U3 to the left, we obtain that V2 is equal to U2 minus U3. And if we plug in the second equality into the first one, so V2 plus V3 is equal to U2, and move U2 to the left, we get that V1 is equal to U1 minus U2. So each VI can be expressed as a linear combination of some UJ's. Consequently, U1, U2, and U3 generate V, because they generate the elements in some basis, namely in the basis V. And since the dimension of V is 3, and we have three vectors U1, U2, and U3, no proper subset of these three vectors can generate V. Therefore, the set U is a minimal generating system, and we know that a minimal generating system is a basis. So this proves that U1, U2, and U3 is a basis of our vector space capital V. So from the definitions, the transformation matrix from V to U consists of the coordinates of U1, U2, and U3 in the basis V, written as columns. And we have these coordinates from the formulation of the problem. So U1 is V1 plus V2 plus V3, so the coordinates are 1, 1, 1. U2 has coordinates 0, 1, 1, and U3 has coordinates 0, 0, and 1. So this transformation matrix is the matrix which we can read column-wise 1, 1, 1, 0, 1, 1, 0, 0, 1. Similarly, from the definitions, the transformation matrix from U to V consists of the coordinates of V1, V2, and V3 in the basis U written column-wise. but we computed this when we expressed v's as linear combinations of u's. So here is our computation. V1 has coordinates 1, minus 1, 0. V2 has coordinates 0, 1, minus 1. And V3 has coordinates 0, 0, 1. So now we collect this as columns into the matrix and get that T from U to V is the matrix which we read column-wise: 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1. And now we can use the base change formula and compute that the coordinates of x with respect to the basis U are equal to the transformation matrix T from U to V times the coordinates of x with respect to the basis V. So we have just computed that the transformation matrix is 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1. We know from the formulation that the coordinates of x in V are 1 to 3. So we compute the product and we get 1 plus 0 plus 0, 1, minus 1 plus 2 plus 0, it's 1, 0 minus 2 plus 3, it's 1. So the answer is that the coordinates of x in the basis U are 1, 1, 1. Problem 4. Consider the following vectors in R3. The vector U1 is 1 to 2. The vector U2 is 2, 1, minus 1. The vector U3 is minus 1, 0, 1. And the vector A, which is 1, 1, minus 1. Prove that U, consisting of U1, U2, U3, is a basis of R3. Determine the transformation matrices from the standard basis in R3 to U and back. For the element B in R3, such that the coordinates of B with respect to the basis U are 1, 1, minus 1, determine the coordinates of the vector A minus B in the standard basis and in the basis U. So in our collection bold U, we have three vectors, U1, U2, U3, and we know that R3 has dimension 3. So the number of vectors is correct, and to show that this collection is a basis, we just then need to show that the determinant of the matrix, which we obtain when we write our vectors as columns, this determinant should be non-zero. So here is the computation of the determinant. So this determinant is equal to 1 times 1 times 1 plus 2 times 0 times 2 plus 2 times minus 1 times minus 1 minus 1 times 1 times 2 minus 1 times 0 times minus 1 and minus 2 times 2 times 1. So we have 1 plus 0 plus 2, 3, plus 2, 5, 0, and minus 4 is 1. So the determinant is 1, this is non-zero, and this implies that our vectors U1, U2, U3 form a basis in R3. From the definitions, the transformation matrix from the standard basis to the basis U consists of the columns giving the coordinates of U1, U2, and U3 in the basis E, in the standard basis. So we just take those coordinates from the formulation of the problem and write them as columns in the matrix. So this transformation matrix from the standard basis to U is a matrix 1 to 2, 2, 1, minus 1, minus 1, 0, 1, read column-wise. We also know that the transformation matrix in the opposite direction is just the inverse of this transformation matrix. So to determine the transformation matrix from U to the standard basis, we simply compute the inverse of this matrix using the standard algorithm. We write our matrix, vertical line, and then the identity matrix. And now we reduce this big matrix to a row echelon form using Gauss elimination. So we have 1 here in row 1, column 1. So we use it to eliminate everything else in its column. So we multiply row 1 with minus 2 and add to row 2. We multiply row 1 with minus 2 and add to row 3. So row 1 remains the same. Row 2 becomes 2 minus 2 is 0. 1 minus 4 is minus 3. 0 plus 2 is 2. 0 minus 2 is minus 2, 1 minus 0 is 1, and 0 minus 0 is 0. And row 3 becomes 2 minus 2 is 0, minus 1 minus 4 is minus 5, 1 plus 2 is 3, 0 minus 2 is minus 2, 0 minus 0 is 0, 1 minus 0 is 1. So in this matrix in column 2, here we have minus 3 and here we have minus 5. The easiest way is to multiply row 2 with minus 2 and add to row 3. And then we can also swap these two rows. So we get a matrix where row 1 remains the same. The original row 2 here becomes row 3. And now the new row 2 is as follows. So 0 plus 0 is 0. 6 minus 5 is 1. Minus 4 plus 3 is minus 1. 4 minus 2 is 2. Minus 2 plus 0 is minus 2. And 0 plus 1 is 1. So now we have 1 here. So we can use it to kill everything in its column. So we subtract twice row 2 from row 1, and we multiply row 2 with 3 and add to row 3. Row 2 remains the same. Row 1 becomes 1 minus 2 is 1, 2 minus 2 is 0, minus 1 plus 2 is 1, 1 minus 4 is minus 3, 0 plus 4 is 4, and 0 minus 2 is minus 2. And row 3 becomes 0 plus 0 is 0, minus 3 plus 3 is 0, 2 minus 3 is minus 1, minus 2 plus 6 is 4, 1 minus 6 is minus 5, and 0 plus 3 is 3. So now we have minus 1 here, so we simply change the sign in the last row. So the first two rows remain the same, and the last row simply changes the sign. And now we have 1 in row 3, column 3. We can use it to kill everything else in its column. So we add row 3 to row 2, and we subtract row 3 from row 1. Row 3 remains the same. Row 1 becomes 1 minus 0 is 1. 0 minus 0 is 0, 1 minus 1 is 0, minus 3 plus 4 is 1, 4 minus 5 is minus 1, and minus 2 plus 3 is 1. And row 2 becomes 0 plus 0 is 0, 1 plus 0 is 1, 1 plus minus 1 is 0, 2 plus minus 4 is minus 2, 5 plus minus 2 is 3, and 1 plus minus 3 is minus 2. And now the matrix here on the right-hand side is exactly the transformation matrix from the basis U to the standard basis E. So we just copy this matrix. So this transformation matrix is equal to 1 minus 2 minus 4, minus 1, 3, 5, 1 minus 2 minus 3, read column-wise. Next, let us compute the coordinates in the standard basis of the vector A minus B. We know that the coordinate map respects addition and multiplication with scalars, so this is equal to the coordinates of the vector A in E minus the coordinates of the vector B in E. The coordinates of A in E are given in the formulation, but we have the coordinates of B in U from the formulation. So to obtain coordinates of B in E, we use the base change formula, and instead of these coordinates, we write the transformation matrix from the standard basis to U times the coordinates of B in U. And now these coordinates are in the formulation, and the transformation matrix is computed on the previous slide. So we get the vector 1, 1, minus 1 minus the transformation matrix from the previous slide, which is 1 to 2 to 1 minus 1 minus 1, 0, 1, times the coordinates of B in the basis U, which are 1, 1, minus 1. So the first summand we just copy, and then we compute this product. So 1 plus 2 plus 1 is 4, 2 plus 1 plus 0 is 3, 2 minus 1 minus 1 is 0. So we get 1, 1 minus 1 minus 4, 3, 0. And 1 minus 4 is minus 3. 1 minus 3 is minus 2, and minus 1 plus 0 is minus 1. So using the base change formula, we now can also compute the coordinates of a minus b in the basis u. So by the base change formula, this is equal to the product of the transformation matrix from u to the standard basis times the coordinates of a minus b in the standard basis. So we have just computed these coordinates, minus 3, minus 2, minus 1. So these are the coordinates of a minus b in the standard basis. And we also see here the transformation matrix, 1, minus 2, minus 4, minus 1, 3, 5, 1, minus 2, minus 3. So now we multiply these two matrices. We get minus 3 plus 2 minus 1. This is minus 2. And then 6 minus 6 plus 2. This is 2. 12 minus 10 plus 3. This is 5. So the answer is that the coordinates of a minus b in the basis u are minus 2, 2, and 5. Problem 5. Consider the following two sets of matrices in the space of all 2 times 2 matrices with real coefficients. The matrix A1, which is 1, 0, 1, 0. The matrix A2, which is 1, 1, 0, 0. The matrix A3, which is 0, 1, 0, 1. And the matrix A4, which is 0, 0, 1, minus 1. The matrix B1, which is 1, 1, 1, 1. The matrix B2, which is 1, 0, 0, 1. The matrix B3, which is 0, 1, minus 1, 0. And the matrix B4, which is 1, 2, 2, minus 1. Prove that the collection A, consisting of A1, A2, A3, and A4, is a basis of our space of 2 times 2 real matrices. Prove that the collection B, which consists of B1, B2, B3, and B4, is also a basis of the same space. Determine the transformation matrices from A to B and from B to A. And for the matrix 1, 2, 3, 4, determine its coordinates with respect to the basis A and with respect to the basis B. Solution: let us recall that we have the standard basis in our space of 2 times 2 matrices consisting of matrix units. So we have E11, which is a matrix 1, 0, 0, 0, E12, the matrix 0, 1, 0, 0, E21, the matrix 0, 0, 1, 0, and E22, which is a matrix 0, 0, 0, 1. So we can now use this standard basis to translate all other elements of our vector space into coordinate vectors with respect to the standard basis. And then we can do what we usually do for all vector spaces. So let us start by proving that the collection A is a basis. For this, consider the coordinates of all vectors in this collection in the standard basis. So if we look at the formulation, we see that the coordinates of A1 in the standard basis are 1, 0, 1, 0. The coordinates of A2 are 1, 1, 0, 0. The coordinates of A3 are 0, 1, 0, 1. And the coordinates of A4 are 0, 0, 1, minus 1. So to show that A is a basis, we have 4 vectors in a 4-dimensional vector space. We need just to show that the determinant of the matrix, which we get when writing the coordinates of our vectors as columns, this determinant should be non-zero. So we have to compute the determinant of the matrix, which we read column-wise: 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, minus 1. So here we see that we have 1 in position 1, 1, so we can use it to kill this other 1 in column 1. So we subtract row 1 from row 3. Rows 1, 2, and 4 remain the same, and row 3 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 0 minus 0 is 0, and 1 minus 0 is 1. So now we have here 1 in position to 2. We can use it to kill this minus 1, which is below. So we add row 2 to row 3. And such manipulations with matrices, they do not change the determinant. So row 1, row 2, and row 4 remain the same, and row 3 becomes 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. So we have the determinant of this new matrix. So now we have this new matrix, and we see that this is a block upper triangular matrix. On the diagonal, we have here a 1 times 1 block with 1, another 1 times 1 block with 1, and here the 2 times 2 block with 1, 1, 1 minus 1. Something above the diagonal and zeros below. The determinant of such a matrix is the product of the determinants of the diagonal blocks. So it's 1 times the determinant of the 2 times 2 matrix 1, 1, 1 minus 1, which is, of course, 1 times minus 1 and then minus 1 times 1, which is minus 2. This is different from 0. And now we can conclude that the collection A of matrices forms a basis of our space of 2 times 2 matrices. Let us do the same thing for the collection B. The coordinates of B1 with respect to the standard basis are 1, 1, 1, 1. The coordinates of B2 are 1, 0, 0, 1. The coordinates of B3 are 0, 1, minus 1, 0. And the coordinates of B4 are 1, 2, 2, minus 1. Similarly to the previous slide, we now have to collect these coordinates into a matrix and prove that the determinant of this obtained matrix is non-zero. So we have the matrix column-wise 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, minus 1, 0, 1, 2, 2, minus 1. So we have 1 in position 1, 1, and we use it to kill everything else in its column. So we subtract row 1 from rows 2, 3, and 4. This doesn't change the determinant. Row 1 is the same, so row 2 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, 2 minus 1 is 1. Row 3 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, minus 1 minus 0 is minus 1, 2 minus 1 is 1. And row 4 becomes 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0, minus 1 is minus 2. Again, we have an upper block triangular matrix with the blocks 1 here, minus 2 here, and the 2 times 2 blocks minus 1, 1, minus 1, minus 1. So the determinant of this thing will be 1 plus 1, which is 2, so the whole thing will be minus 4. So our original determinant is equal to minus 4, which is non-zero. And so we conclude that the collection B also forms a basis of the space of all 2 times 2 real matrices. So now to determine the transformation matrix from A to B, and also the coordinates of our vector M in the basis A, we need to solve the systems of linear equations where the left-hand side is just the matrix consisting of the coordinates of A1, A2, A3, A4. And then for the transformation matrix, we have to solve the systems for the coordinates of B1, B2, B3, B4. Because the transformation matrix from A to B consists of the coordinates of the elements B1, B2, B3, and B4 in the basis A, written as columns. And we should also solve a similar problem for M. So the coordinates of the matrix M in the standard basis are 1, 2, 3, and 4. So we solve all these 5 systems in one go by writing this huge matrix and reducing it to a row echelon form using Gauss elimination. So we see that we have 1 here. We can use it to kill the other one in its column. So we subtract row 1 from row 3. Rows 1, 2, and 4 remain the same, and row 3 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is minus 1, minus 1 minus 0 is minus 1, 2 minus 1 is 1, 3 minus 1 is 2. Now here we have 1 here in position to 2. We use it to kill everything else in its column. So we multiply row 2 with minus 1 and add to row 1, and we add row 2 to row 3. Rows 2 and 4 remain the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is minus 1, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, 1 minus 2 is minus 1, 1 minus 2 is minus 1. And row 3 becomes, we have to add 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. 1 plus 0 is 1, 0 plus minus 1 is minus 1, 1 plus minus 1 is 0, 2 plus 1 is 3, and 2 plus 2 is 4. So now again we have 1 in row 3, column 3, so we can use this one to kill all other elements in its column. So we add row 3 to row 1, and we subtract row 3 from rows 2 and 4. So row 3 remains the same. Row 1 becomes 1 plus 0 is 1, 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus 0 is 1, 1 plus 0 is 1, minus 1 plus 1 is 0, 0 plus minus 1 is minus 1, 3 minus 1 is 2, and 4 minus 1 is 3. Row 2 becomes 0, 1, 0, minus 1, 0, 1, 1, minus 1, minus 2. And row 4 becomes 0, 0, 0, minus 2, 0, 2, 0, minus 4, 0. So now we have to make 1 here in row 4, column 4. So we multiply row 4 with minus 1 half to kill minus 2. So the first 3 rows remain the same, and we divide the fourth row by minus 2. So it becomes 0, 0, 0, 1, 0, minus 1, 0, 2, 0. So now we can use 1 here in position 4, 4 to kill all other elements in its column. So we add row 4 to row 2, and we subtract row 4 from rows 1 and 3. Row 4 remains the same. Row 3 becomes 0, 0, 1, 0, 1, 0, 0, 1, 4. Row 2 becomes 0, 1, 0, 0, 0, 0, 1, 1, minus 2. And row 1 becomes 1, 0, 0, 0, 1, 1, minus 1, 0, 3. And now we can read off the answer from this new matrix. So this 4 times 4 block is exactly the transformation matrix from A to B, because these are the coordinates of B1, B2, B3, and B4 in the basis A. So the transformation matrix from A to B is the matrix 1, 0, 1, 0, 1, 0, 0, minus 1, minus 1, 1, 0, 0, 0, 1, 1, 2, read column-wise. And the last column consists of the coordinates of the matrix M in the basis A. So these are 3, minus 2, 4, 0. So now we do the same thing to determine the transformation matrix from B to A and the coordinates of M in B. We write the vectors B1, B2, B3, and B4 as columns, then the vertical line, then the vectors A1, A2, A3, A4 as columns, the vertical line, and then the vector M. We have this big matrix, and we reduce this to a row echelon form using Gauss elimination. We have 1 in position 1, 1, so we use it to kill everything else in its column. So we subtract row 1 from all other rows. Row 1 remains the same, and row 2 becomes 0, minus 1, 1, 1, minus 1, 0, 1, 0, 1. So row 3 becomes 0, minus 1, minus 1, 1, 0, minus 1, 0, 1, 2. And similarly, row 4 becomes 0, 0, 0, minus 2, minus 1, minus 1, 1, minus 1, 3. So now here we have minus 1, so we multiply row 2 with minus 1. Rows 1, 3, and 4 remain the same, and row 2 just changes the sign everywhere. So now we can use 1 in position to 2 to kill everything else in its column. So we multiply row 2 with minus 1 and add to row 1, and we multiply row 2 with 1 and add to row 3. So rows 2 and 4 remain the same, and row 1 becomes 1, 0, 1, 2, 0, 1, 1, 0, 2. And row 3 becomes 0, 0, minus 2, 0, 0, minus 1, minus 1, 1, 1. So now here we have minus 2 in position 3, 3, and we need 1. So we need to divide row 3 by minus 2. We have no choice. After we do this, rows 1, 2, and 4 remain the same, and row 3 becomes 0, 0, 1, 0, 0, 1 half, 1 half, minus 1 half, minus 1 half. So now we can use this 1 in position 3, 3 to kill everything else in its column. So we add row 3 to row 2, and we subtract row 3 from row 1. Rows 3 and 4 remain the same, and row 1 becomes 1, 0, 0, 2, 0, 1 half, 1 half, 1 half, 5 divided by 2. And row 2 becomes 0, 1, 0, minus 1, 1, 1 half, minus 1 half, minus 1 half, minus 3 divided by 2. Here we have minus 2 in position 4, 4. We can use it to kill 2 in position 1, 4. So we add row 4 to row 1. After that, we have to divide row 4 by minus 2 to make 1 in position 4, 4. Rows 2 and 3 remain the same, while row 1 becomes 1, 0, 0, 0, minus 1, minus 1 half, 3 halves, minus 1 half, 11 divided by 2. And row 4 becomes 0, 0, 0, 1, 1 half, 1 half, minus 1 half, 1 half, minus 3 divided by 2. And now we use this 1 in position 4, 4 to kill this minus 1 in its column. So we add row 4 to row 2. Rows 1, 3, and 4 remain the same, and row 2 becomes 0, 1, 0, 0, 3 divided by 2, 1, minus 1, 0, minus 3. And now we can read off the answer from this matrix. So this 4 times 4 block is the transformation matrix from B to A, and the last column are the coordinates of M in the basis B. So the transformation matrix from B to A is equal to 1 half of the matrix minus 2, 3, 0, 1, minus 1, 2, 1, 1, 3 minus 2, 1, minus 1, minus 1, 0, minus 1, 1. We read them by columns. And the coordinates of M in the basis B, so this should be B, is equal to 1 half of 11 minus 6 minus 1 minus 3. Here are some additional problems and questions. Question 1. Determine the coordinates of 1 plus x minus x squared in the basis x minus 2 to the power k, where k is 0, 1, and 2, of the space of all polynomials of degree at most 2. Question 2. Extend 1 plus x minus x squared to a basis of Rx sub 2. Question 3. A matrix M is called symmetric if M is equal to M transposed. Find some basis in the space of all symmetric 2 times 2 matrices and extend this basis to a basis of all 2 times 2 matrices. Question 4. Extend the vector 1 minus 1 minus 1 to a basis of R3 and find the transformation matrix from this basis to the standard basis. Question 5. Let n be the set of all real polynomials of degree at most 3, consisting of all polynomials which are divisible by x squared plus 1. Show that n is a subspace and determine some basis and n and the dimension of n. Thank you very much and see you next time.